Okay, so this next question around translational motion, we've got two discs, disc A and disc B, that's attached together with this bit of string, and we've got different masses, and A hits B, and then after the collision they're going off at right angles to one another, and we don't know what their velocities are, but we do know that they're travelling at right angles to one another. So the first question is to show that the speed of the centre of mass of the system is 0.521 metres per second. Show where you're working. Remember, that's what you're getting marked on, and don't use this in your calculation. Your answer should come out as this. So to do that, I'm going to use this equation here, where the velocity of the centre of mass is equal to the total momentum. So it's the momentums of A and B added together, divided by the total mass. So I showed the deriving of that equation from 2 questions ago. So that's it there. Okay, so we're taking the centre of mass equation and dividing both sides by t, and it comes out as this. You can think of it like this: if you have the velocity of the centre of mass, if we take the masses of the system over to this side, the velocity of the centre of mass times the total mass of the system is the total momentum, and that's equal to the sum of the 2 momentums. Okay, so that's another way, or another place this equation comes from. Anyway, let's get to answering the question. I have to use this scenario up here because there is enough information here to work it out. We don't have enough information down here to work out the answer to the question. I just realised that I didn't draw my string in, which is probably quite stressful for the pucks, because if they didn't have the string, they'd be going off in their own directions to infinity. Be pretty lonely. Okay, so momentum 1 is m1v1, and momentum 2 is m2v2 over the total mass of the system. So here we have 0.517 times 1.21, and we're going to add to it, well, that one's stationary, so I'm just going to add a big fat 0 there. And then the total mass of the system is 0.517 plus 0.684. Cool. Going to bung all of this into a trusty calculator again and see what we get. My eldest daughter Nova is getting right into calculators at the moment, and she always puts like lots of numbers in and then asks me if the calculator's right, and I tell her, yeah, the calculator's right, the calculator's better at maths than me. She still, thinks that I might be better than the calculator at maths, which is really nice of her. Cool, so there's the answer, 0.521 metres per second, and it's to the right, by the way, which is in the same direction as the momentum of A up here. Just check that I got the, spoiler alert, that's the next question. 0.521. Oh yeah, good, I can give myself a tick. I love show questions. Well done me. Okay, the next question. The discs collide after the collision. They are moving at right angles to each other. Disc A receives an impulse of 0.250 Newton seconds. Oh, interesting. What was that? Disc A. So the impulse on disc A must be in that direction, eh? Delta P on A. So the change of momentum on A must be in the opposite direction to the change of momentum of B. Okay, and those two impulses must be the same because it comes from Newton's third law. Remember that impulse, change of momentum, is equal to force times time. And Newton's third law tells us that the force on A from B must be equal to the force on B from A. So those two forces are the same in magnitude but opposite in direction. And the length of the collision is the same. So B is in contact with A for the same amount of time as A is in contact with B. It wouldn't make sense if it was anything else. Anyway, back to the question. The discs collide, and after the collision they are moving at right angles to each other. Disc A receives an impulse of 0.250 250 Newton seconds. Right, so I'll write that in. So that happens back here at the collision point. Show that the speed of disk B after the collision is that, and explain your reasoning. Okay, so I've already gone into my reasoning. Here. And my reasoning is that the impulse on A must be equal to the impulse in B. Okay, so delta P A equals delta P B. I'm just ignoring the negative thing for now. Technically it should be negative 0.50. Okay, so the impulse is the same. Cool, and then I can just use the equation to work out the change in speed. Oh, okay, yes, I can't use this equation. I don't need force because I don't know time, but I can use the regular momentum equation. So delta P equals P final minus P initial. We know the final momentum is going to be the change in momentum, because before the collision B had no momentum. If we know that's the change, then that must be the momentum B has after the collision. So 0.250 minus the initial, which I just said was 0. Okay, so that is the final momentum. Cool, so that is the momentum of B after the collision. Kg meters per second, and I'll give it a direction this time, it's that way. Cool, which means the velocity the momentum is equal to mass times velocity, which means the velocity is equal to PB divided by the mass, 0.250 over the mass of B, which is 0.684. Meters, what am I doing? Velocity, meters per second. Cool. And again, this is a show question, so the answer is 0.365 meters per second. Cool. And my reasoning is this part up here. What I love about show questions like this, if you've finished the exam early, you've got time to go back. If you didn't know how to do it, you've got enough numbers here, just mash them all into your calculator until you get the right answer, and then write down whatever working it was that spewed out the right answer. Alright, C. The discs continue to slide until the cord is fully extended. When this happens, both discs change their speed and direction. By considering the forces that act on the discs, explain why the momentum of the system must be conserved. Okay, so this is that same thing that I've said in previous questions. It's about external forces. So since the force on A from the string will be equal to the force on B from the string, because of Newton's third law, all of those forces are internal to the system. They don't come from outside. It's not due to friction or to gravity or something else like that, or wind that causes the string to become tight. It's all to do with forces from within the system. So in this case it's the tension force on the string as these two objects move further apart, which is an external force. So if there are no external forces acting, then the centre of mass will travel at a constant velocity. So the discs continue to slide until the cord is. When this happens, both discs change speed and directions. By considering the forces that act on the discs, explain why the momentum of the system must be conserved. Okay, yeah. So these forces are internal to the system. So momentum must be conserved. Cool, that's it. And on to the last question.